Okay, so we'll be starting with the week four's summary. Uh, it is in continuation with last week's lectures only. Uh, we'll discuss some of the interrupt processes, their priorities, how they can be masked, how interrupts can be enabled, disabled. Just, I think it will be clear because sir discussed it thoroughly, just to make sure that everyone understands. Then a bit of sim and rim instructions, triggering levels, I think. Yeah. So to start with the 8085 non-vectored interrupt processes. Uh, Yeah. So what is an interrupt first and foremost? Can anyone tell me what is an interrupt?
Microprocessor CPU is working, doing its work, and suddenly, if some uh, trigger is coming to stop its work and do the work which the interrupt has triggered. So,
So yeah, basically a main program is running. Instructions of main programs are running, and MUP is executing those instructions. And in between, if some urgent instruction is to be implemented, then interrupt signal occurs, and MUP will respond accordingly, whether that interruption is important or not, right? So that's
yes,
so how do so one of the ways we differentiated between interrupts was vectored or non-vectored. So by vectored, are you guys interested in giving answers? Then we can have it in a discussion mode. So what are the vectored interrupts?
it
You
is
can just keep talking. Huh.
a vector interrupt means it will be having its specific call locations. Um,
Yes. So once the interrupt is occurred, the MUP is supposed to, if it is to entertain the interrupt, it will go to the ISR location of that interrupt, right? So if
yes, ma'am.
the ISR interrupt is predefined, that interrupt is called vectored interrupt. And if the ISR is not assigned, if the location of ISR is to be provided by the peripheral device or chip that has incurred that interrupt, then it's called non-vectored interrupt process, right?
Yes, ma'am.
So yeah, these are the non how you define non-vectored interrupt processes. Then we have issues in implementing INTR interrupt. So INTR interrupt, we know it's a non-vector interrupt, right? So the issue is kind of for how long that interrupt should keep, I mean, keep poking the MUP so that it'll execute or it'll acknowledge that interrupt has occurred. Because let's say some instruction is going on, MUP is executing some instruction, and in between that instruction, INTR occurs, right? So for how long INTR has to be there, that signal has to be there for the interrupt for MUP to acknowledge it. So by common sense, it has to occur for the longest possible time for which the microprocessor takes to complete one instruction, right? So the longest possible instruction is that we know is call instruction takes 18 states, right? So discussed this in class. So if say interrupt this INTR occurs at the starting of call instruction, and if it remains until the completion of all the T states that it takes to execute that call instruction, that means at the end of that call instruction, the MUP can see that this in only then it will check if there's some interrupt, right? So it can acknowledge or ignore whatever be the case. But the important thing is it has to remain there for those longest period of the time cycles, right? So that is why I took the this example that call instruction, which is the longest one, we which takes 18 states. So MUP will have to be MUP will check it only after it the call instruction is completed. So INTR has to be there for at least that many number of T states, right? I hope that is clear.
Yes, yes, ma'am.
Yeah.
Yeah, ma'am.
Um, yeah. So next is multiple interrupts and priorities. Let's say there are, I think we discussed this in previous class also, so you all can answer this one. So what if multiple interrupts occur simultaneously? What will happen then?
Then it's 1915. You don't have any new notes. According to the priority of the internet.
Yeah, so interrupts are
It's
assigned the same
1950.
priority, right?
Have any new notification?
So according to their priorities, the new people entertain those interrupts, right? So yeah, what else? And the priority encoder is encoded with the priority orders, and like the way you set the chips in the priority encoder, the chips will be entertained according to those priorities, right? If say two chips are there and both of them are simultaneously incurring some interrupt, depending on what pin they're connected to priority encoder and what pin is then connected to the interrupt pin of the UP, they'll be acknowledged, right? Their interrupts will be acknowledged.
Yes.
I think that's okay. So then is the maskable interrupts. So we know that RST 5.5, 6.5, and 7.5 are maskable. You can mask them according to, I mean, you can disable all the interrupts with the DI instruction, but if you want, like, for the time being or for some period of your main program, you don't want a certain pin to disturb your main program, then you can mask them individually, right? So 5.5, 6.5, and 7.5 can be individually masked using the sim instruction. I can discuss the sim instruction, but I hope you guys will help me with this. I mean, the discussion part. Okay, so sim. So how can you, if this is, these are the 8 bits that are fed to accumulator for the masking. Which ones do I do correspond to the masking of these RST 5.5, 6.5, and 7.5 for sim instruction?
0, 1, and 2.
0, 1, and 2, right? 0.
Yeah.
This is
0
the
for
0,
5.5, 1 for 6.5, and 2 for 7.5.
right? So yeah, this is right. Okay. So, as you might be knowing by now, that SIM is a multi-instruction, what do you say? Multi-purpose instruction, right? So, these three interrupts can be the RST 5.5, 6.5, and 7.5 can be masked through SIM instruction, but there are other bits also, right? So, I think we can have somewhat decent discussion of this sim instruction. So can we, I think serial data was also discussed, right? Serial transmission. So what are these first two bits, like D7 and D6?
D7
Ma'am,
is SOD and D6 is
D7,
SDE.
right.
Serial data
So
out, and
serial out,
this is enable serial data,
serial
D6.
data enable, serial out
Yeah.
data and serial data
Serial
enable,
data enable, yeah.
right?
Mm. Yeah.
This one
ma'am,
is don't care bit. What are the remaining two bits?
One is mask, fourth
That
bit is mask set enable, and fifth bit
7.5.
is R7.5.
This is mask. What is it? MSC.
MSc.
Yes, mask element. Right? So, since sim is a multi-purpose instruction, we can do multiple things with this sim instruction. You can mask the the interrupts. You can reset the 7.5 interrupt pin flip-flop, and you can enable the serial data transmission. Right? So for the masking part only, we need to discuss these four bits first. So see, if these bits are M 7.5, 6.5, 5.5 or 1, they'll be masked. If they are 0, they won't be masked, right? But if this MSE is not enabled, which means if uh, MSC is 1, only then your masking will be applied to the interrupt pins. If this MSC is not 1, then this is kind of don't bother condition. Whatever be the D0, D1, D2, they won't be entertained, right? All the interrupts will be masked. All the interrupts won't follow the masking pattern that you're applying to the interrupts, right? So, yeah. So, yeah, if I have, let's say, uh, okay, let's first discuss R7.5. So, what is R7.5? Does anyone want to answer?
It is a specific bit to reset only R7.5. It is not depend upon MSC.
Yes, but why do we need to reset R7.5? RST 7.5.
Please repeat the question, ma'am.
So this bit is this R7.5 is used to reset the RST 7.5 pin, right?
Yes.
My question is, why do you need to reset R7.5? Others are not, I mean, there's no other bit is available for these 6.5 and 5.5. Why 7.5?
If we want to stop this flip-flop by force, the 7.5 RST 7.5, then we need this.
That is understood. I'm asking why do we only have it for 7.5? Why not for 6.5 and 5.5?
Is that because that RST 7.5 interrupt is the only interrupt that has memory? Is it for that?
Yes. I mean, it has memory, but it's not because of that. The reason of this, I mean, the answer of this question is the reason why it has memory. Now, why does it have memory? I
Since
mean,
it is level,
the flip-flop,
sorry,
huh?
since it is edge triggered,
Yes, yes. So RST 7.5 is the only, I mean, completely
Age
only
trigger
interrupt
trap.
with, yeah, only edge trigger. Trap can have both, but 7.5 is the only one which is edge triggered. So edge triggered means whenever this clock cycle, I mean, this edge is going too high, then this interrupt will be, I mean, poking the MUPI, right? So let's say for the time being, if this RST 7.5 is masked for this, let's say this is the clock. Okay. And RST 7.5 is masked until here, and after this cycle, you decide to unmask RST 7.5. Okay. But while this was masked, this is here, RST 7.5 is masked right now. But during this cycle, 7.5 occurred. Let's say, okay, it is masked, The MUPI won't acknowledge it, but the signal for that the interrupt occurred, and nothing will happen. MUPI won't entertain it. It is masked. But what happens is after this cycle, you decide to unmask this 7.5. And since it has memory, you know that once this interrupt occurred, the interrupt will be there in that memory, that flip flop we have for 7.5, right?
Yeah.
So if now in next cycle I unmask RST 7.5, would you like to entertain, or would the MUPI like to acknowledge that interrupt which occurred when RST 7.5 was masked? I mean, it was masked for a reason, that whatever interrupt occurs in that duration of time in 7.5 pin, it doesn't want to acknowledge it at all, right? But there is that in the memory point, in the memory the storage flip-flop that is connected to RST 7.5, it will contain the contents when this occurred when it was masked, right?
Yes.
Yes. So after it is unmasked, MUPI or the programmer doesn't want it to acknowledge the previously occurred interrupt.
So then we have to stop by force this.
Yes. So you have to
That's why we need that.
not stop, you have to reset that
Reset that. Yeah.
RST 7. Yes. That
Mm.
is why you have this reset for 7.5. Am I mean,
Yeah. Yeah. Clearly understood. Mm.
did everyone understand what I was trying to say?
Yes,
Right? Since RST 7.5 is the only edge triggered and it can contain the contents of the previously occurred interrupt, and we don't want to acknowledge that previously occurred interrupt, or you can choose to acknowledge it or not acknowledge it, right? Depending on what you choose this bit to be. Correct?
Yes.
But we want to have that provision to reset this interrupt pin, so that whenever the need comes, you don't entertain the previously occurred interrupt. You may choose to not for it to be zero so that you entertain the previously occurred interrupt, but there is a provision and you need it. You understand why you need it, right?
Yes.
Right? So that is why we have this reset for 7.5. What else? Don't care. It can be anything. We don't care. Now, these SOD and SDE. So, SOD is for sending out the serial data, right? Whatever be the contents of this SOD bit, it will be sent. If it contains zero, zero will be sent serially. If it is one, one will be sent serially, right? But since we know SIM is a multi-purpose instruction, and there might be times when you are only interested in masking the interrupts and you don't want to send anything, and you have to, I mean, it's a 8-bit thing, right? You put all of the 8 bits to the accumulate. If you're supposed to put something 0 or 1 in SOD, and since you're not interested in sending some serial data, and only interested in masking the interrupts, what will you do to prevent sending that serial data?
we'll write 0 to SD. So
Right. So the SD pin is SDE pin is important because SIM is for multiple used for multiple things, and if you don't want to send anything serially, you just put this 0 so that whatever be the contents of SOD pin, you are not interested in sending serially, it won't send anything. Okay, that is the purpose of SD, serial data enable. Then SOD just transmits whatever it contains. I think that covers SIM, right? Any questions on this? No. All right.
no,
Then we have
one. Sorry.
rim.
If I keep
So
1 in SOD
I'm
and
not able to hear. Can you please speak loudly?
if is it audible now, ma'am?
Yeah.
Okay. So if I keep 1 in SOD and
Uh-huh.
then if I make the SDE to toggle, like for say 100 microsecond SDE to be 1 and
Mm-hmm.
next 100 microsecond SDE to be 0, if I
Mm-hmm.
keep toggling SDE bit, will I see the same toggling in SOD, madam? Like what happened before previously, I had kept 1 and kept
Yeah.
SDE high so
Mm-hmm.
that I can see 1 in the SOD.
SOD contents of SOD are not changing, you're saying.
Yeah, content of SOD is not changing, but I'm enabling and disabling the SDE
Uh-huh.
for say 100 microsecond.
Okay.
So whenever SDE is high, then
Mm-hmm.
I understand that whatever values there in this SOD bit will be sent out using the SOD pin.
Yes.
And
So what? Uh-huh.
assume it's 1,
Mm-hmm.
and I'll be sending 1 out for 100
Mm-hmm.
microsecond.
Mm-hmm.
Later, if I disable the SDE,
Mm-hmm.
I'm keeping SOD as 1 but SDE as 0, will the output in the SOD pin go low?
SOD won't send anything, no?
So
If
send
SD,
won't send.
meaning of SD1 is that the whatever the data or the content of SOD is, it will be transmitted,
Okay, so if
right?
I connect the SOD pin to an oscilloscope and
Mm-hmm.
probe the pin,
Mm-hmm. It won't send anything since SD is enabling the serial data transmission.
okay, so it won't be sending anything. Mean will it be 0 volt? Like if I measure the volt, like I assume it's like either 5 volt or 0 volt.
Uh-huh.
So the SOD, I expect that.
Zero, I mean, from what I understand, zero will be sent only when SDE is enabled, right? If SOD contains zero, then it will be sent. I mean, I've not thought about it. This is what I understand right now.
Okay, okay, ma'am.
Yeah, because it won't send anything.
Okay,
I think, yeah, I'll see. Uh, Maybe we can discuss it next week. I'll mark it.
okay, ma'am. Just toggling the SOD instead of
Mhm.
varying SOD data. If I keep SOD as 1 and toggle the SDE,
Mhm.
so what I thought was like whenever SDE is 1, then SOD should be 1, and
But
whenever
that would mean you are sending zero, but you're not sending anything.
yeah, we are
If
not
S,
sending, but
yeah,
to outside world when
what
some
will it
see outside
yeah,
world
what
will be
will the
seeing 1
output
and
of
0. Yeah.
oscilloscope will be? Yeah, I understand your question,
Okay.
but
Yeah.
yeah, let me think about it.
Okay, ma'am. Thank you.
Okay. Yeah. Moving on to rim instruction. So sim is just a set interrupt mask. It's called set interrupt mask. Then rim is read. So with sim instruction, you set the mask or whatever, all the functions that sim is supposed to do. With rim instruction, you're just you can get out the status of those of the mask bits or all of the pending bits. Like if I just draw it like sim, this is rim, right? So first one is here in data I 7.5. Now, if you remember from sim instruction, it also had N 7.5, 6.5, 5.5. Those bits are called, uh, or you call them as if you want to mask the instruction. Here, these D0 to D2, they're called mask ED. So they contain the information of whether these interrupts 7.5, 6.5, and 5.5 are already masked or not, right? You're just reading. Yeah. So these are the bits for the information on whether they are masked or not. This is interrupt enable. Like it was uh, initially told that I think it was told it. Interrupt enable is whenever you enable this pin, whenever it is high, your interrupts can occur, and whenever you lower this pin, interrupts cannot occur. And these are 5.5, 6.5, and 7.5. These are the information of all the pending interrupts, right? Let's say you same case if simultaneous interrupts occurs, and let's say both of 7.5 and 5.5 occurred. And since due to higher priority, this 7.5 was entertained by the MUPI, which means that 5.5 interrupt is still there. So this bit will be high if this situation was there, and which would mean that there's a 5.5 interrupt that is pending, right? That's it. Think, yeah. Yeah, the interrupt occurred but was not serviced by MUPI. So these bits will give information about that. And the serial and data will receive the data, right? That SOD was serial out data. This in SIM. In RIM, we have SID, serial in data. If the whatever is the serial data incoming, it will come to this bit, D7 of the RIM. Yeah, I think it covers RIM. Any questions on this? No, that you can go on. Yeah, these are triggering levels. I think everyone is familiar with the triggering levels. RST 7.5 is edge triggered, 6.5 and 5.5. This is 5.5 are level triggered, right? And trap can be both, depending on the need. Next we have, yeah, pending interrupts. Yeah, I think I just discussed it with the rim instruction. Internal interrupt priority, we discussed this last time also. Trap has the highest priority, RST 7.5, 6.5, 5.5, and the least is INTR. Trap is of highest priority, but it has lower priority than the hold of the direct memory access, right? Then what is direct memory access? Is the data transfer between two peripherals directly without the involvement of the microprocessor. Then we have serial input output interfacing. Yeah, identify. Okay, so uh, yeah. So the device, there might be multiple devices connected to the MUPI, and while the serial transfer is to take place, before that MUPI has to identify which device is selected for the serial transmission or reception. Then read write enable read or write lines are to be enabled for whatever is the operation that is to be done serially. And yeah, that's it. So Next, we move on to synchronous and asynchronous data transmission. So synchronous is used for the high-speed transmission, more than 20 bits per second, and asynchronous is for the low speed transmission. What else? And the in serial data transfer, this baud rate is important because it dictates for like on what rate the the data is to be transmitted or received, because your receiver and transmitter have to be in sync, have to know at what rate the transmitter is transmitting, so that receiver can receive it at that rate. If if there is some mis what do you say miscalculation of this rate of, then you can get receiver can receive rubbish data, because it'll, let's say, transmitting 8 bits, receiver thinks it's 5 bits. So you see there'll be miscommunication, right? And whatever it receives won't be a meaningful data at all. So that is why baud rate is important. Baud is bits per second, important for serial data transmission also. I think you might have seen this baud rate. If you work with the Arduinos or such microprocessor boards, microcontrollers, then you set, if you are transmitting data from microprocessor to some other inter peripheral device or something, then you set that baud rate, right? If you have worked with it, you'll know what I'm talking about. So if there's a mismatch between your transmitter and receiver, if the baud rate set at the transmission end is different from the baud rate set at the receiver's end, you don't get data at all, or you get some rubbish question marks or nan values or whatever, right? That is why baud rate is important. Yeah, that's it. So, any questions on this? All right. So, sir also discussed about transmission as an example, transmitting a character serially. Does anyone have problem understanding that, or should I move on with error checking? So basically, just an overlooked view. So for to transmit a character, we all know all the characters are in ASCII codes are some combination of some bits, right? So he took example of what? A, I don't know. Say some character is to be transmitted, and it has combination of some bits in ASCII, right? So to transmit this character serially, what the MUPI does is it'll transfer these bits in that character array serially, and the receiver will receive it. It will decode it there, whatever is the combination there according to ASCII. It'll decode and see whatever was, interpret what was sent, like getting the meaning out of that zeros and ones, right? That's about transmitting character. Then we had error checking. Like there might be some errors. Like if you're sending whole lots of bits, baud rates are what can be thousands of bits per second, right? So there might be some errors, and to check the errors, there are these two ways: parity checking and checksum. Parity checking you can do it for a small chunk of data, and checksum is used for if you have large amounts of data. You can't do parity checking on every byte of data, right? So for that we have checksum. Yeah, that's it. So does anyone want to Tell me how checksum works. Just to be clear that you all know. What is the like basic procedure of how checksum works? How this process of error checking, checksum checks the errors. Anyone? Okay, so after sending the data, let's say you have a list of bytes and they are to be sent to some receiver serially. The transmitter will sum all the bytes, right, and save it and send it as the last byte of data, right? Sum of all the bytes and send it as the last byte of data. And on the receiver end, receiver will sum all of them. Okay, no. Transmitter will send the negative of 2's complement of that sum, right? It will send that 2's complement at the end of data. Receiver will sum all the data that it received and it will sum it with that last byte of data that it got. And if since the transmitter sent it the negative of that sum, and receiver will just uh, add all the data that it got, and it will add that last bit of data and its own sum. If it comes out to be 0, then there's no error. If it's not 0, which means the sum that negative of the sum that transmitter sent and the sum of receiver are not matching, which means there's some error. And yeah, that's how it checks, right? So this is just the name of standard for serial communication introduced in 1960s, I guess. Then you have software controlled serial transmission, software controlled serial reception. I think we have discussed SOD also, SID also. What else? All right. I think I'm done with the summary. Does anyone have any questions regarding any of the lectures, or should we move on to questions? Am I audible?
We can move on to questions.
Okay, sure. And there were some programs also discussed. If someone has difficulty understanding those, we can discuss them later. Right? Or are you guys all clear with the program? Then, I mean, that way we can spend more time on the problems. Otherwise, we'll just do them faster. Oh, my question one is missing. Okay. So, yeah, I think we'll do it the same way you guys do this. Write in the chat box or speaker, and we'll see. Okay. So, you have to match column X with column Y. It's right. So, which of these characteristics match with the interrupts given in the column X? So,
Non-maskable input.
Both
trap is non-mask. RST 6.5,
It's,
level sensitive.
level sensitive.
level sensitive. NTR,
NTR is non-vector interrupt.
NTR is non-vector, yes.
And RST
LS15 is
7.5
edge
is
sensitive.
sensitive.
Edge sensitive. So, which one of these?
Option D, ma'am.
1, 3. No, 1 is 3. B can't be. Okay, D. Yeah. 1, 3, 2, 1, 3, 4. Yeah. So D is the correct answer. Clear?
Yes, ma'am.
Yes, ma'am.
Oh, what do we have? Question 2. Interrupt vector table ranges over.
Option C, ma'am.
C, that is
C.
00002 00FF.
000H2 00FFH.
Yeah. Okay. And please interrupt in between. We're doing interrupts. Interrupt if you don't understand any of the question or the answers, right? So RST7 is which one of the following? Restart instruction that begins the execution of program. 1 byte call to memory address this. 1 byte call to memory address 007H and or hardware input. Okay, let's do it one by one. Is it a hardware interrupt or software interrupt?
It's a hardware interrupt.
It's RST7,
Software interrupt, ma'am.
software interrupt, right? So we know this is not the answer straight away.
Yes.
It's okay.
Yeah.
Sometimes whatever we get in the INTR pin, right? That's from an external device,
Mm-hmm.
and the
It can go
RST7,
to.
yeah, RST7 opcode can be sent from an external device.
Yes, yes. But
But the best answer is something else, so we can strike
yeah,
out this.
ambiguous option. Sorry. Okay, so here, yeah, I don't want to. Okay, so yeah. Is it a restart instruction that begins the execution of the program?
No,
No.
No, which means it has to be one of these, right? So we have to either you remember the address where it goes to, or you calculate it right away. So where will the RST7's memory address will be? ISR memory address? Can we calculate it?
0038H.
Yeah.
0038H. Option B.
Yeah. 0038H. Does anyone want to know how we got to this? I mean, we
7,
discussed it last time.
7 into 8.
Yeah.
7 into 8,
7
that
into
will
8 is
get,
56.
that is
So
decimal.
it's
We have
it's
to convert that into
into hex value.
hex.
Hex number, which is, I don't know,
It is
48 plus 8. 48 is what?
That is
3,
3, 8, ma'am.
8.
3.
Yeah.
Yeah.
8. Yeah. H.
Right?
Yes.
So it goes to 0038H. Right? Any question on this? Okay. Next question. Again, match the columns with these interrupts. So RST 5.5 is, I think it's the same question. One bit different. Yeah. RST
As the
5.5 is
5.5 is
anyone?
Ma'am, am I audible?
Yeah, yeah. Now you're audible.
Yeah. RST is 5.5 level sensitive, level triggered.
Level triggered, right?
6 is software.
So software.
7.5 is age triggered.
What is 4.5?
It is edge
4.5,
and level trigger.
Obviously, I mean. The option
Both.
is third, but what is RST 4.5?
It is a trap interrupt.
Yeah. So initially, trap was named RST 4.5. If you
Yeah.
right, and
Yes.
later
So
it
both
was
age and level trigger that will be.
yes. So this is actually trap. If anyone didn't know it, later it was renamed to give it a special, I don't know, treatment because it is special. It can't be highest priority interrupt. So what is the answer? 1224. C, I
C,
guess.
C.
Yeah,
Yeah, ma'am. C.
C. Yes, C is the correct answer. Okay, next. INTR must remain active for how many T states? We just discussed it.
17.5.
18.5.
Think
17.
about it.
Since call instruction is the longest instruction, so it consists of 18 T states. So
Mm-hmm.
at 17.5 T states itself, the INTR will be recognized by microprocessor.
Yeah,
So
so,
option B,
so why is it not 18.5? Call is how many T states long? 18,
18.
right?
18.
So after 17.5, let's say these are 17, and this is where uh, 18th, 18th T state ends. So this is where 18th T state ends. After 17.5, I mean, after this, MUPI is free to, I mean, read out or entertain the interrupts if anyone is, if any signal has occurred during, after the instruction. I mean, here there is nothing that it is occupied with. So after 17.5, originally call is 18 states. It will be completed here only, but MUPI can identify any interrupt if it has occurred. So ideally 17.5 T states, not 18.5. After 17.5, it is, I mean, kind of done with the instruction. Okay. So correct answer would be 17.5.
Yeah, ma'am.
Okay. Next is multiply these two numbers stored in memory locations. Okay, it's a bit of. Huh. So we are given two numbers, 03 and B2. Both have 8-bit and stored at 2200, 2201. And we the multiplication is to be done by repetitive addition. The result is to be stored at memory locations at 2300 and 2301H. Yes, so we want to know what is the output in these two locations. So how will we do it? So we are given that 2200H memory location contains what? 03. This is the address. This is the memory data. And 2201H contains B2H. And we are told that the multiplication is to be done by repetitive addition, and we are supposed to identify what is the output in these 2300 and 2301. Anyone wants to try?
Yeah, ma'am. Trying.
So basically, repetitive addition, you're not going to repeatedly add 03B2 times, right? What we'll do, uh, result will be actually three times. You'll have to add B2 three times. That will give you the multiplicated result, right? So B2 plus B2 plus B2. Can anyone tell me what will be the result in X?
2 plus 2 plus 2 is 6, and b plus b plus b is 33 in it says 11 in decimal, so 33 in decimal, so it's 21 in hex, so 1, and then carry is 2.
Oh,
That's
right. I mean, this should be the answer.
0216.
We're not doing the program here. You're just supposed to see what will be the output, right? So this should be the actual result after this addition, right? And we know bits are stored as uh, data is stored as 8 bits. Like one memory location will have these two 0 and 3, and totally they make up 8 bits, right? 1 byte.
Yes. Yeah.
So the results that will be stored will be this 1 6 at one location, and since there is 2 here, it will be stored as 0 2 at other location. Oh, I don't have answer in. No, we have answer. Okay, so this is the lower order result. This is the higher order byte of the result. So where will this 16 be stored, and where will this 02? If this is 2300, 2301. Remember, higher bit of result will be stored at higher address, and lower will be stored at lower one.
Yeah. So 16 will be stored
That
in
is the rule that
2300.
is followed.
16 will be stored in 2300, ma'am, and 02 will be in 2301.
Yes. So this will be our answer. Was that clear how we arrived at this?
Yeah,
I
ma'am.
mean, this is the convention that is followed, that lower bit is stored at lower address. Lower address means this lower number. Since this is the higher, this is greater than this 2300, it will contain the higher order of the result. Okay. Which gives us the correct answer as B. Yeah.
Yes, ma'am.
Okay. So, to which pin the external DMA controller sends the control signal in 8085?
Hold
Hold,
pin, ma'am.
hold.
Hold.
And what happens after hold? And yes, this is the correct answer. DMA sends the control signal to 8085. And then what happens?
And then microprocessor will send and hold acknowledge signal.
Yes,
So,
microprocessor will acknowledge that it has received the signal, right? Then it will send the acknowledge signal. Okay. Uh, Next, which interrupt in oh, an interrupt in which the external device supplies an address as well as the interrupt request is called. The ISR address is sent, and the request is also sent by the device.
Should be non-vectored, but I don't know whether that can be called as designated.
Yeah, that's what I was
What
thinking.
is the meaning of designated, ma'am, actually?
Designated, the ISR is, I mean, how do you explain it? Designated. The address is designated to some uh, memory location. Means that. Let me see.
Then that will be the answer, maybe.
Ah,
Huh.
where here I think the options are not clear. Okay, I'll leave this one. Let's see. Let me just check. Mm-hmm. I don't know. I think I'll get it next time. I'll get the answer of this next time. For now, let's just leave it. Should be, I don't know. Okay. Next question. How many 8-bit characters can be transmitted per second over 9600 baud serial communication link using synchronous mode of transmission with one start bit, 8 data bits, 2 stop bits, and 1 parity bits? Okay. So, what do we understand with this of the question? That 8-bit characters are to be sent, that all, which means all the characters that are sent, let's say it's A, B, C, or whatever, each of this is represented by combination of 8 bits, right? So these characters which are represented by 8 bits are to be transmitted serially. That part we understand, and they are sent at this baud rate. Baud rate is 9600, and we're using asynchronous mode of transmission. And what all bits are to be sent are the one start bit, 8 bits of the data, which will represent the character you're sending, 2 stop bits, and 1 parity bit. Understood? Any confusion in the question?
Then total 12 bits are transmitted at a time.
Ah, so in this mode, the transmission is taking place with these number of bits. Like we have, just a bit, we have 2 start bits, right? Then we have 8 bit of data.
Answer B, I think, ma'am.
And let me,
Okay, okay.
yeah.
It's
So,
one start bit. No?
uh-huh.
It's one start bit.
One start bit. It's a
Okay.
start bit.
I heard it as two start bits. Okay. Sorry.
Oh, sorry. Yeah. One start bit. This is 4 plus 4, 8. 2 stop bits and 1 parity bit. What will be here? So this is start bit. This will be the data. This will be parity bit. Survival parity bit. I just said I put an arrow here. I send parity bit here and bits here.
No, stop should stop the transmission. After that, we should not send it.
Right. So
What?
anything that is to be sent should be between start bits and the stop bits. So uh, parity bit should come before the stop bits. This should be parity, and after your complete set of bits that you're sending is complete, then you send your stop bits. Because if the receiver receives stop bits before your whatever you're sending like if the stop bits were these, it won't consider this one as your parity bit. For the receiver, the data is complete here. Okay. Yeah, so total number of bits that are to be sent is 12, 1, 8, 1 and 2, right? And baud rate is 9600, which means 9600 bits per second are sent. So number of characters, what's the question? The number of characters that are sent. So for one character, it takes 12 bits, and we are sending bits at 9600 bits per second.
Yeah.
That are transferred will be 9600 bits per second per 12 bits, because 12 bits represent per character, which will be, what is it,
800,
800,
ma'am.
right? 800 is the correct one.
Yes.
Ma'am, I have a doubt. Like they asked how many 8-bit characters can be transmitted per second over 9600 baud rate.
Huh.
So we need to add start bit, stop bits, and parity bit with it, or
Yes,
only?
because since the mode of transmission is asynchronous, right? There is transmitting end, you can send just the 8 bits, but the receiver has to know when your data is starting, right? When it is, so I think normally the serial of the receiver, it is high, and when it goes low, I mean when the start bit goes low, the data that is receiving goes low. This is considered to be as the starting of the data. Okay. For receiver to know that your data is starting, this line has to go low, and this represents the start bit. This low signal here represent your start, so that receiver knows that the data is now going to come. Okay.
Okay.
And then you send your data, whatever be the data, 101, whatever. So this has to be there because receiver has to know that the data is now being sent, right? So you need start bit. Whatever data you're sending, you have to send. Those are those 8 bits. This parity bit is for, remember that error checking.
Okay.
So you send that parity bit, the transmitter is, with this parity bit, it is sending the information what parity is being followed in the this data, whether there are odd number of ones, whether there are even number of ones. Depending on that, this parity bit will be 0 or 1.
Okay. Okay.
I mean, that is the convention that in this serial transmission, it is, I mean, they could have said you're not sending parity bit. Then you would have just 11 bits to send. This won't be here.
Okay.
So with every data, you send the parity bits for the sake of that error checking thing, if you remember. Right? And once you've sent the parity bit, then receiver has to know that the one complete data, that is character in this case, that the data is complete now. You have received the parity bit. Then whatever is the stop bit, stop bits can be any combination of bits, 0, 1, whatever. Like there are 2 bits, so you can have 4 combination of stop bits. There's a convention chosen for the serial communication. Uh, so whatever be the stop bits, once your data is sent, you have to send those stop bits. So the receiver knows that the whole chunk of data, or the one character, which is represented by this string of bits, is complete, and now you need to interpret whatever has come. So these
Okay.
start and stop bits are for the receiver to know that now data has started to come, or now the data string is complete and I need to stop reading. or obviously you might have more than one characters to send, right? Like here, how many? 800 characters are being sent. So after these stop bits, if there's another start bit, like if you want to, if the MUPI is sending next character, then receiver has to differentiate between, okay, this is the first character, now I've got another start bit, which means I've got another set, another character to read or receive. Differentiate between the data and to know when to start reading or when to stop.
Okay.
Yeah. Yeah. Okay, so yeah, answer was 800 characters were transmitted. Next is interrupt control logic does what? Anyone? Does it manages interrupts? Mm.
C is not right.
Uh-huh.
Accepts interrupt acknowledge signal. That's, to me, it's not right.
Why not right?
Accepts interrupt acknowledge signal. Oh, it's an external interrupt controller.
Yeah.
Okay, it's not an interrupt control logic inside 8085.
Yeah, that is what's happened.
I thought
Just a minute.
if the logic
Mm.
inside 8085, then it should generate the
Yeah, just
interrupt
the,
acknowledge.
yeah.
Okay, if it is an external interrupt controller, then that also this B manages interrupt acknowledge signal.
So
Uh,
basically, interrupt acknowledge. Okay, I should have explained the. So, complete what the question was supposed to be. Uh, what all things are done by these interrupt control logic signals. You have INTA, right? So yeah, I don't know. As for me, it manages interrupts like that diagram. If you remember, that Sir drew. Uh, let's draw it. So you have those priority encoded chips, right? And MUPI has these lines INTR, INTA, or what all. Then you had, say, you have different devices connected here through these priority encoders. So, okay. So yeah, these are the devices. These are the encoder chips through which they are connected to uh, MUPI. So, yes, yes, preparation. Yeah. So to me, the answer is all of these because the interrupt acknowledge or interrupt logic control logic manages interrupts. It manages interrupt acknowledge signals, and because MUPI has to, I mean, this priority encoder will see which device is sent and what all lines should be sent to these AD 85 to 83, right? And after getting these, um, yes, someone has raised a hand. Question. According to priority of these devices, they are the signal is sent to MUPI. MUPI then acknowledges it through INTA. right? And then it sends the acknowledgement signal. The signal is sent to the device, and then it does it. So yeah, I think the question is not clear. Okay, so basically, it manages interrupts. It acknowledges signals and accepts the interrupt acknowledge signal from this MUPI, right? So, all of the above. Apologies for the ambiguous question. Someone raised a hand. Do you have question? Okay. On to the next question then. What is the at the end of ISR instruction? ISR is interrupt service routine.
Return instruction.
Return.
That one, right?
Yeah.
Once the interrupt is served, the MUPI should move back to its main program. And for that, we need return instruction to pop out the address, the that was in PC, whatever. Next is question. Uh, yeah, I think we have discussed what is the correct ordering of priority.
Option A, ma'am.
Then.
Hmm. So, which of the following statement is correct? Asynchronous serial data transfer is used for data transfer rates of less than 20K,
Ma'am, your slide
and
is not
synchronous
up.
for.
It's 2021.
Is the screen visible?
Now it's
Now.
visible.
So, yeah, we discussed this earlier. Which one of or what is true for these statements? Statement 1 and 2. Asynchronous is used for data transfer less than 20K, and synchronous used for greater than 20K. I mean, you remember, I guess. So yeah, asynchronous is used for less than 20K bit baud rate, and synchronous is for greater than 20K. Okay, so both are correct.
As you
Mm,
told, like it's for some RS-232, you were referring this was found in 1962 or something. So
uh-huh.
this statement may be valid like 20 years back, and UART, the asynchronous data transfers, right? Nowadays we have even in MBPS at least like uh,
But we're studying 8085, no?
yeah, yeah, maybe
With
to
yeah, with the reference to with context. Which of the statements do you think are true?
okay.
Yeah. Okay. All right. Next question. Is it the same question? Yeah. Um. hmm, Same question. Sorry for that.
Question 14, we'll select none of the above option.
Asynchronous is. Oh yeah, not same question. Yeah. Asynchronous for greater than 20? No. And synchronous for it's written greater than 20. Synchronous is for greater than 20, right? We won't select D. So statement 2 is correct, right?
Yes, ma'am.
Alright. So contents of accumulator is PAH after execution of sim instruction. What will happen? We can do this one. So BAH, what is B? B is 10. 1 1. Oh. A is 1010. So if accumulator is this and you execute a sim instruction, what will happen? First of all, what are these masking bits? This is mask enable, MSE, MSE. This one is reset 7. This is don't care. This is serial data enable. This one is serial out data. So what will happen after sim is executed?
I think reset
Reset
RST, RST 7.5 flip flop memory.
Mhm.
Um,
This one
This
is
one is
for
for
Hmm.
hmm.
So
So
this is
this is
high,
high,
which
which
means
means
7.5 will
7.5
be
will be
reset. Correct? Anyone?
anyone.
Also, we have some options for 6.5. Can you check if these can be correct or not?
Am I
Yeah, your voice is very low, but I can hear you.
am I audible now?
Still low.
Still low.
It's 2026.
Option C, how it could be, ma'am? Reset RST 6.5 flip flop memory.
Correct. I'm just asking you if
No,
whether they can be correct or not.
no, it won't be.
This
Option
can be
C.
correct.
Yes.
This is, we know this one is correct. So RST 6.5 is unmasked. Is it unmasked?
No, ma'am, it is masked actually.
It's masked, right?
Yeah.
So yeah, wrong. Just wanted to check if you understand. So yeah, 7.5 is masked, and since this SD is low, there won't be any serial data transfer. So this doesn't matter. This already is don't care. Yeah. So this is the correct answer. Well, yeah, that's it from my side. If you have any questions or doubts, you can ask me. We have some time. And I needed one suggestion. When I upload these PPTs, I have uploaded them for like all the undone PPTs, all the work that I write or whatever. In case I erase them, do you want me to upload them as it is or the plain ones are okay?
Ma'am, pen ones are okay.
Okay, fine. That's what I thought. I was just thought of asking you. So, okay, someone saying with written. In that case, I can upload both if you want. Right? You're able to access the folder, the whole folder, right? So I can upload both. Okay, then if there are no doubts, that's it from my side. And if there are no doubts, and I asked if anyone had problems with the programs. If you have problems with the program, if you want me to discuss them, I can discuss the programs. Otherwise, yeah, that's it.
Thank you, ma'am.
I have one doubt in the assignment
Uh-huh.
one assignment 3, week 3, assignment 3, you have access.
Yeah, I can open it if you'll give me 1 minute. Weekly assignment. Good weeks.
Yeah, and that's
Mm.
question number 9.
Mhm. Yes. Question 9 is ah,
Which of the following
uh,
statements?
which of the following statements regarding call and return is false? Yes.
So if you can move that to the presenting screen now, is it possible, or you can
Okay,
share that
so
just
what is the doubt? Correct answer is not acceptable, or
yes.
any of the other options?
Correct
Okay,
answer is not acceptable. So the correct
so
answer they had given is D.
D.
Answer D.
Yeah.
So in
So D is
the program,
first return instruction may appear before the first call instruction.
yeah, that's possible, right? Because RST is 0, the
Mm-hmm.
vector location is 0000. I
Mm-hmm.
can very well have one return instruction inside that 8 bytes.
Yeah.
And so the very first instruction can be written like if you take the very first memory location as
Getting.
00000 to FFFF, the
Uh-huh.
very first location, the zeroth location, I can have a return.
Yes.
And the call can be say in 8000 where my main program is, or where I want to call any sub program.
Yes.
So logically that statement, like I can have a return before my first call instruction.
Okay.
Yes.
Okay. So question was which one is false? Okay. Yeah. Getting. So if you have return and first, but first return instruction may appear before the first call instruction. If you have return at 000, 00 just resets the MUP, right?
That's the vector location for RST 0.
Huh.
So the 8 bytes from 0 to 7 are reserved for RST 0.
Yes.
So when if I have assume my main program starts at say 8000, location 8000, where
Mm-hmm.
if I have RST 0 in my program, then it
Mm-hmm.
will jump to the 0th location, the corresponding address for reset 0.
Uh-huh.
I can return from the, I can do nothing, like I can have 2 or 3 no op, and then I can have a return instruction, and I can return
Mm-hmm.
from there to my main program.
Yes, but if it goes to 0, it means it will reset. It won't, I mean, what do you call it? Reset means everything starts over, right? It won't be implementing instructions, executing instructions.
No, the RST 0, the 0th location is nothing but the call vector location for RST 0, the software
Mm-hmm.
interrupt, right?
Yes.
So I think reset location, it's depends on the manufacturer. So when a reset comes, we can.
Generally, I think it's 0 as far as I can remember.
Okay, fine.
Maybe I'll see through this your query and maybe I'll write it in the forum.
Yeah, sure, ma'am. Because the RST vector location, right? As we discussed now, also like RST 7, it's 7 into 8, it's 56.
Yeah.
Similarly, for
I'm
RST
getting.
0, yeah, it's the starting location is 0.
But then it won't, if you have first return.
No, I can have written little later also. I mean, even in RST 7th vector location, whatever that 38H, right? I can have a return, but there may not be a need that the like call should be first, then only return should follow. Uh, like
Okay, I'll see if there's some exception in this.
okay.
So yeah, any other doubt? All right then. Okay, you can leave. Thanks for joining. Good night.
Good night, ma'am.
Night.
Night, ma'am.